Hello everyone, welcome again to a new Deltares webinar, the 13th Deltares webinar, and the second one in a series of two dedicated DELWAQ webinars. Last month was a webinar by Michel Jeuken on code compiling of the DELWAQ open source code. This month we have invited Jos van Gils to present a webinar about principles and notable applications of the DELWAQ software. Please note that during the webinar you can ask your questions to the panel. We have a panel of experts available and you can ask textual questions to them using the questions box. Jos, please, if you can start your presentation. Good luck.
Thank you very much, Roderick. Good morning and afternoon, everybody. On this slide you see the subjects that I want to cover with you in the next hour. After my introduction, I'll discuss with you the equation and the variables. I'll talk about units transporting media, about numerical methods, about processes, about mass balance output, and finally, in more or less detail about working with processes in DELWAQ. That depends a little bit on the amount of time that we will have available for that. First, I would like to share with you who are hosting this webinar. My name is the first one on this list, and the next one is the person, Roderick, who introduced you to the webinar. The people answering the questions are Jan van Beek, Michel Jeuken, and Christophe Tihange. All of them members of the DELWAQ support team and experienced users of DELWAQ. For you listeners, there are a few assumptions I made while preparing this webinar. First, I assume that you know something about water quality modeling. Second, this will be a very practical webinar, so it comes in handy if you have some practical experience. Because it's part of the open source momentum for DELWAQ, it's also useful if you have some affinity with programming, or at least an interest to get some affinity with that. I haven't assumed that you're familiar with Delft 3D WAQ or Sobek WAQ, so I basically deal with all to understand the full picture. We organized this webinar because as of very recently, D-Water Quality or DELWAQ has become open source, and our objective with this webinar is to whet your appetite, to show you what you can do with DELWAQ and to make you aware of the supporting information that is available here at Deltares. The previous webinar that was hosted by Michel about a month ago provided you details on compiling, on downloading, compiling and running the D-Water Quality version on Windows. If you haven't attended that webinar, or if you don't remember everything, please visit our website to find the related information, and I think the full webcast is available there. Then the first question is, what is D-Water Quality? And I'm going to answer it in two ways. This is the first way. It's a computer program developed in 1982 by Leo Posma, that's the gentleman on the top right part of this sheet. Continuously developed further in the past 30 years by the staff here at Delft Hydraulics and later at Deltares under the guidance of Leo. Open source this year and has been linked to many hydrological, hydrodynamic and water allocation models. We have, before we went open source in the past 20 years, more than 100 licensees worldwide, and this is just a wild guess, there must be more than 1,000 applications of this software. For rivers and lakes, for seas, lagoons and deltas, for canal systems and for urban water systems. And a footnote, the reason why I show you the picture of Leo Posma, that he's retiring soon, and he's very happy that just before his retirement DELWAQ has actually become open source. The next way to explain you what the D-Water Quality or DELWAQ is this slide. Basically it's a program that eats an input file, a program consisting of two parts. First part DELWAQ 1 exe, second part DELWAQ 2 exe. DELWAQ 1 exe swallows the input file and produces some reports for the user one report with the extension LST and the other one with the extension LSP. The difference between the two I will come back to later. The first program feeds the next program that carries out the calculation and produces output files. Report files, output files giving you results at output stations, map output for animations, and mass balances output. All of this you can find in our documentation. A few words about the input file. The input file is basically one text file, which is partly keyword oriented. And two very important features that decide the readability and the usability of this file are the user-defined comment character, often selected to be the semicolon. And that means that in this file you can put your input, put the comment character, and next put your comments to increase the readability of the file. And also very important is the unlimited use of include files. So from this master input file you can refer to any other file by just including the word include on the file name. And that's also a handy feature to organize your input. In software packages like DELWAQ and Delft 3D, there are user interfaces that produce this input file for you. This webinar doesn't discuss that element of working with DELWAQ. I will start discussing with you mostly from this input file onward. That brings me to the basic equation and key variables in the program code. DELWAQ is a water quality model, and it simulates one or more state variables, or substances as we call them. The number of state variables or substances is called notot in the code. On this slide and on the next one I will indicate anything which refers to the source code with this bluish color. So whatever you see in this color is a direct reference to the source code. Those substances that you model can either be active, that means they are moved around by currents and by dispersion, by advection and by dispersion. They can also be inactive, and that means that they are not transported by currents and dispersion. In the arrays of the software you have first the active substances numbered 1 to nosis, followed by the inactive substances numbered nosis plus 1 to notot. What the program is doing is basically two things. First, transport those substances within your model schematization. And this transport is in most cases the same for all active substances. Doesn't really matter if a substance is salts or BOD or oxygen. They all move around in the same way. And the second aspect that the program is dealing with are processes, decay processes, transformation processes, etc. And these are typically different for the different substances that you model. So that's where you will notice one substance behaving differently from another one. Next, DELWAQ works with finite volumes or segments. I've drawn one here. And that's how the basic equation is defined for these segments. Every segment has a volume with a unit length to the power 3 as a function of time. And here again you find the relevant array in the source code. You will notice that noseg, the variable noseg, is the number of segment in your calculation. There is concentrations within a segment of the notot state variables as a function of time. Here you find the relevant array, two-dimensional array, with one dimension the number of substances and the next dimension the number of segments. And finally, every segment has a horizontal surface area, if applicable as a function of time. And the equation that the program is solving is that the change of the mass of a substance within the segment equals the transport plus the loads, pollution loads that you put in, plus the processes, and the unit is mass per time. And this change of mass is stored in the array deriv, D-E-R-I-V, that you will find in the source code. This equation is solved, and that means that DELWAQ calculates the mass either as a function of time or as a steady state, and this is the relevant array. And as a final step, the concentration of the substance that you model in the segment is calculated as the mass divided by the volume for active substances, or the mass divided by the surface for inactive substances. DELWAQ therefore uses the mass as its primary variable and not the concentration, and that means that it's by definition mass conserving. There is no way that mass can get lost in this calculation process. Next, a model doesn't only consist of segments, it also consists of connections between segments, and that's what I try to draw here. Two adjacent segments, I and I+1, and they are linked together at what we call an exchange. An exchange from segment I to segment I+1. This administration of the connections of the exchanges is stored in this array here. At an exchange, you have to define how much water is flowing from one segment to the next, indicated by the symbol Q, unit length to the power 3 per time, volume per time that is. You have to specify the contact surface area between the two segments, length squared. This is the array name. You have to specify the dispersion coefficient, either as kind of a default in this array or as a function of space in this array. I haven't mentioned yet that this variable NOQ indicates the total number of exchanges in your model. So the total number of places where two segments have a contact with each other. Finally, you have to specify the from length and the to length in this array, indicated here, again at the exchange surface for DELWAQ to be able to calculate the transport. The active transport is calculated as the flow, cubic meters per second usually, times the concentration. The dispersive transport is calculated by this formula. That's basically the law of Fick, and the transport is proportional to the gradient of the concentration in a direction perpendicular to the contact surface. And that's, for example, why these lengths are required. It's important to notice that DELWAQ does not require any ordering of these exchanges. You can administrate them in any irregular or regular fashion you would like to do that. That means that DELWAQ basically has an unstructured grid. And that also means that DELWAQ has no problem to connect to finite volume or finite element models. Next subject, I'm now going to tell you a little bit more in practice on how we model, and I will do that a little bit by talking about the units and transporting media. DELWAQ is using arbitrary units for mass, for distance, and for time. Evidently, we often work with meters, grams, and seconds, but that's not absolutely required. There's also a fixed ratio between the unit for time used in the transports and the loads part and in the processes part. And that is because commonly people calculate transports using the second time unit and processes using the day time unit. So you can specify that ratio. A note for later on is that the processes library assumes that the time is indeed measured in days. An example of how you can play around with these units, and I will also use that to demonstrate to you how DELWAQ works, is that you can, for example, use the normal way of modeling where you specify a water volume, you calculate time in seconds, you work with water flows, and you work with water concentrations. You can easily replace that by using particle masses as a carrying medium, count the time in years, and replace water flows by particle fluxes, and not calculate water concentrations but solid phase concentrations in grams per gram. And that's just an example of how you can use DELWAQ to make a 100-year timescale sediment model. I'll show you that in a minute. That model has been set up for this estuary. It's a model that goes back to the late 80s when computation time was expensive and people were not using a lot of segments. In this case, we were using 14 segments from the upstream side of the estuary towards the downstream side of the estuary. And the question that arose at a certain point is the sediments in this estuary are polluted, and how long will this bother us if we clean up the estuary today? And we couldn't calculate 100 years in the classical way, so we applied this transformation to span the 100-year time horizon. We looked at transport, not at processes, and we didn't look at water as a carrying medium, but we looked at fine particles as a carrying medium. We neglected the interaction between the particles and the water as a kind of a limit case. And we used 100% as an initial concentration, so you could consider that as 100% polluted. And we looked at what would happen to those 100% after 100 years of simulation. I'm going to show you now this simulation. But this is my input file. This is a batch file, basically a DOS-based batch file to run DELWAQ. That's something that Michel tackled the last time. And I will run this input file. And you first see DELWAQ 1 reading the input file, giving me some warnings, but happily not any errors. And then you see the calculation. And now we have simulated 100 years in the snap of a second. You see that DELWAQ has produced a huge number of output files. I will be looking at this one in particular, the history file, the HIS output that will show me the results in the segments as a function of time. I use a SOBEC-based viewer of this file. And here you see the substance, the percentage of polluted sediments. I show you all the segments and I show you the initial condition. You see that there is 100% of polluted sediments in the estuary. After 10 seconds of computation time, which represent 10 years because of the mapping, the transformation that I did, it looks like this. You see that at the upstream end of the estuary all the pollution has gone, but in the middle it has stayed, but also on the sea side the input of fresh marine sediments has been cleaning up the sediments. And similarly you can look what happens after 20 years, when in the middle of the estuary still 80% of the pollution is remaining. And not to bother you too long with it, after 100 seconds, equivalent to 100 years, the estuary is about clean, with about 1% of pollution left in the middle of the estuary. Well, this was a demonstration of a DELWAQ simulation, and it illustrates maybe a little bit better when we look in the input file in a little while, that you have to couple DELWAQ to something that calculates the transporting medium. So if you use water as a transporting medium, somebody is going. DELWAQ is not calculating that, that's input. So you have to couple to a hydrodynamics model or something similar. This involves the segment and the exchanges administration, the segment volumes, the exchange flows, the areas and the length. In 3D models, this also involves vertical dispersion, and optionally you can derive the water temperature, the salinity, the shear stress, etc., also from another hydrodynamics or sediment transport model. Then, if you have coupled DELWAQ to a hydrodynamics model, we routinely do this check. We model a substance called continuity to check if the input is correct. We give it an initial concentration of 1. We make all the boundary conditions equal to 1, and that means that the solution should also be 1. And if that is not the case, that indicates that the water balance contains errors and that the hydrodynamics model has some problem. And it also means that this deviation from 1 will be reflected proportionally in all substances that you simulate. So you do not want this deviation to be significant. Okay. You may have noticed in the previous example that there was also something called cont, or continuity. This is because the input to this simulation was specified manually, and then you can use that also to check if there have been no errors. The initial values for this continuity were 1, and also after 100 years of simulation, still it was all 1, and that means that the input is correct. There's no problem with the specification of the carrying medium, the transporting medium. I'd like to show you also as a kind of an example what the input file looks like in this small example. This is the input file. What you see at the first line is here this comment character that you can specify as a user, which can be used afterwards to indicate comments. Now this is an example with a lot of Dutch comments, so it may not be very clear to you what is here. And I've used that for all the files indicating the silt balance that is underneath this simulation. And you see here in the folder where my input file is stored that there is this subfolder that I'm referring to, where I'm storing all the files that I refer to from the input file. This can be a way to organize your input in a way that allows you to keep the overview and to not to be bothered by all information at the same time. Okay, this is all I wanted to tell you about this input file. There is a manual describing in detail the format of this input file, and at the end of the webinar I'll come back to that. After having seen the input file, I want to mention briefly that because of the fact that DELWAQ is being used now for 30 years, it has been coupled to a lot of different hydrodynamic and water flow models, and on this slide you see 12 examples of the most illustrious programs that we have been working with. I think this one is an interesting one for many of you, but maybe also this one, and maybe this one. Evidently also the Deltares models are among this list. Something about numerical methods. I told you before that DELWAQ basically does two things for you. One is solving the transport equations, solving the transport, and two is processes. With regard to transport, there are different methods to solve the equation. Our main program contains 23 alternative methods to solve the model equations, which we have developed in the past 30 years. All of them are still there. You will find them if you download the code. Although some of them are not used often, that means there might still be errors in there. Some of them have effectively been replaced by others, and some are actually not really meant to be used outside a research context, but you never know when you need them, so that's why we left them there. The differences between the methods are related to the discretization of the advection term. You can do that basically upwind, which is not so accurate but very stable, and central, and then you have a problem with wiggles, which you can try to suppress by using limiters, and that's what the different schemes are doing. The schemes differ, the methods differ with respect to their time discretization. You can use upwind schemes, and those are the easiest ones, but they have a stability criterion, and that means that you may have stability problems and problems to achieve valid solutions. There are implicit methods, more complex but unconditionally stable. And there are mixed methods, and interesting is that we have self-adapting methods that switch between the upwind mode, which is potentially more accurate, and the implicit mode, which is the stable one. And they do that in a smart way so that you keep stability and optimize accuracy. There are dynamic solution methods in steady states, and finally there are different methods to solve the equations, either by direct matrix inversion or by iterations. These are the methods that we recommend from practical exercise. This slide discriminates between 1D and 2D problems and 3D problems. That means here we don't have a vertical dimension or a vertical gradient, and here we have them. The first level is the unconditionally stable method, and at the same time the most inaccurate method. At the other end of the spectrum, there are the methods that are potentially unstable, which have a stability criterion, but are potentially very accurate. Those methods are named here by the number, and these numbers you can trace back to the user interfaces or to the manuals. In between, I would like to mention especially these self-adaptive methods that are in between, that try to optimize the accuracy, maintaining an unconditional stability. And I will illustrate that by an example. Oh, sorry, the example comes in a minute. I also wanted to mention that there are steady-state solvers, and again I differentiate between 1D and 2D and 3D, where we have iterative solvers, which are the more powerful ones, and direct matrix inversion solvers that are the more accurate ones. But in practice, the direct matrix inversion solution methods are not useful in 3D problems because they use too much memory. The example I wanted to show you is from a model we made in Hong Kong from the Pearl River Estuary and Hong Kong coastal waters, developed for the Environmental Protection Department in Hong Kong in 2007. The related report can be downloaded from the internet via this link. With this model we calculate a 3D salinity distribution. Here you find the number of segments. And we do that initially in the most accurate way, using the second order flux corrected transport scheme, number 12. And we use that as a benchmark, like this is the optimal accuracy that we can achieve. This simulation requires a time step of 1 minute, and whatever you do with the time step makes the simulation unstable. And if you do that, the simulation takes 37 minutes in this example. What we do with the other tries that I will present you in a minute is we will use this most accurate version as a benchmark, and we will calculate the difference between an alternative method and this method and present it in this way, calculating the difference from the benchmark and presenting it on this scale. And in this case you see that everything is green, which means a difference of 0. So this is the ideal picture. This means optimal accuracy. So I tried the number 16, the number 22, and I compared them to the number 12. And these are the results. Number 12 is the most accurate one, but it's unstable if the time step is bigger than 1 minute, and it takes 37 minutes. Number 16, the unconditionally stable scheme, if used with a time step of 10 minutes, it takes only 5 minutes to run, but this picture shows you that the accuracy is poor. And if you increase the time step to 30 minutes, that gets worse. This one we didn't try. But the number 22 shows interesting results. With a time step of 5 minutes, for example, which is 5 times larger than the original time step, the simulation time reduces from 37 to 9, and the accuracy is almost perfect. You can increase the time step and go to shorter, faster simulations and gradually lose more accuracy, as demonstrated by these pictures. But still, this simulation, for example, is much more accurate than this one. So here you see the power of these self-adaptive schemes, which allow you to maintain most of the accuracy with only a fraction of the calculation time needed. And that can be attractive in practical situations. I also think this is a good example of showing you how you can play around with the different schemes and find for yourself the optimum equilibrium between accuracy and fast runs. Okay. This brings me to the subject of processes and how you can use DELWAQ to model processes. Back to the basic equation, the one that I showed you before. The change of mass is transport plus loads plus processes, and we're going to look at processes now. So sources, that means substances appearing. Sinks, that means substances disappearing, and transformations, meaning one substance becoming another one. And as I said before, these processes are typically different for one substance than they are for another substance. Numerically speaking, there are a few things you should know about DELWAQ and its processes. First, we only have this processes and processes library available in dynamic solvers. So as soon as you want to calculate steady states, you're lost. There are some plan B solutions for that, but I won't go into that in this webinar. Second, the processes term is always solved explicitly in the numerical methods. Whatever method we are using, so all the different methods that I just showed you, they're all explicit with respect to the processes. And that means that the processes can cause instabilities. And an example is for a first order process described in this way, then this will be your stability limit. In practice, that means that with time steps up to 1 hour, you are almost never in trouble, except maybe for coliform bacteria, if they die very quickly, or very strong sedimentation resuspension phenomena. But in most cases, you will not have a problem. Okay? This slide shows you the multitude of processes and substances available in our processes library. I'm not going to discuss them with you one by one. You can find that in the manuals that are available. Another way of listing these processes and substances is simply by this list. We have tracers and salinity, bacteria, BOD and DO, suspended matter and the associated sedimentation and resuspension processes. We have nutrients, organic matter, phytoplankton, grazers, metals, organic chemicals, and we model the sediment explicitly. I will tell you a bit more about phytoplankton and about sediment modeling. For phytoplankton, we have two different ways to proceed. First way is the simple way, we call that dynamo, and it has up to 2 groups of pelagic algae, and you have to fix as a user the properties of the algae, how fast it can grow, how much nutrients it needs, how much light it needs, etc. As an alternative, we have bloom, what we call bloom. There you are allowed to model up to 15 species of algae and species groups of algae, which can be pelagic or benthic, and the properties of those algae can vary according to the environmental conditions. There's a solution algorithm inside that optimizes biomass and primary production by varying the properties of the algae within certain limits that you have to specify as a user. And that means that your algae can actually adapt themselves to light limitations or periods of nutrient limitations and change their properties accordingly. And 2 ways of sediment modeling that we support in DELWAQ. First way is the S1, S2 approach. This is a state variable IM1 in organic matter 1, let's say silt particles. And if we want to model the sedimentation and resuspension of those silt particles, we have to model also the content of the sediment with respect to those silt particles. And in this approach we do that by defining an additional inactive state variable called IM1S1 in sediment layer S1. If you want 2 sediment layers, you can also use IM1S2. And in this approach, the sedimentation process is actually mimicked by a process, a transformation process, which transforms this variable to that variable. And for the resuspension, you transform this variable to that variable. And okay, that's one way of doing it. Another way of doing it is what we call the DELWAQ G approach, G for generic. There you model the sediment as different layers or segments. In this example I have shown 3 segments representing the sediment, and in every segment we model the state variable IM1. And in this case, processes like sedimentation and resuspension are actually transport processes, which transport a substance from a water segment to a sediment segment. And that also means that the stability of this process is determined by the solver and no longer by the processes condition that I discussed before. For the rest, you can read about these two approaches in our manuals. Then, why does DELWAQ have a processes library? That's because during those 30 years that we have been modeling with DELWAQ, we found that often an application requires tailor-made choices. So every next model looks a little bit like the previous one, but excuse me, but not completely so. And so we made the processes library to be able to selectively reuse processes from a previous application, but with some flexibility. So we have the flexibility to model a certain concentration or to force it. So if you, for example, if you want to model the decay of BOD, we know that that is temperature dependent, and you have the flexibility to either specify the temperature as a forcing function or to model the temperature. The processes library allows both and nothing changes. Another way of flexibility is that we didn't want the processes to depend on the way you specify your input. To specify the input as a function of space and time or as a constant should not make a difference for the process. And finally, the processes library allowed us to use alternative submodels without changing other submodels. As a trade-off, as a spin-off of the processes library, we organized the processes fluxes in a structured way, and that allowed us to include them in our DELWAQ mass balances output option. And this, I think, is an appropriate moment to discuss with you briefly DELWAQ's mass balances output option, which we think is a very powerful feature for you as a future user. The mass balances output option shows you in the unit mass per time the accumulation of substances, the loads, the boundary fluxes, the fluxes to and from subdomains, and the processes fluxes. And you can make those balances for subdomains of your model domain. You can do that for individual state variables or for clusters of state variables, like total nitrogen or total phosphorus. You can do it in lumped way, so without detail or very detailed, time dependent or integrated over the total simulation. And there is an extensive manual available on how to use this feature. This slide shows you an example. An example for an observation area. Where's my mouse? Okay. An observation area, in this case called Humen. A substance oxygen. You see here the storage or accumulation term. I left out some boundaries. You see some pollution loads, which are not actually present here. I left out the transports from one subdomain to the next one, and I zoomed in on the processes. And here, for example, you can see which processes are affecting the oxygen balance. And in this particular case, you see, for example, a negative number here. This is the nitrification substance consuming a substantial amount of oxygen. Another example is here, primary production of algae, of green algae and diatom algae, producing a substantial amount of oxygen. And here you see reaeration as a process, again producing a huge amount of oxygen. What you can do with these numbers, show you a few examples. One example is here. You can use it to make a complete system balance, in this case for nitrogen. So here the person who has made this picture, I think it was Jan, has shown you a balance for a total model area, including the inflow of nitrogen, atmospheric deposition, the sinks of denitrification, the outflows to downstream areas, but also the interaction between the water column and the sediment. And you see in this example that this sediment-water interaction is, quantitatively speaking, of the same order of magnitude or bigger as the inflows from upstream. And this helps to provide an overview. Another thing you can do with these balances is make a time series of processes. In this case, I have produced the sediment balance for phosphorus. And you see here per month a number of processes related to the sediment and related to phosphorus. This is the flux from the water to the sediment, like sedimentation of particulate matter. This flux here is the return flux from the sediment to the water, concentrated very strongly in the summer. These dark bars are the burial fluxes. That means phosphorus buried to the deeper sediment layers and not coming back. And the white part is the storage or the accumulation in the sediments. And the blue line is the net effect of the sediment on the water column. And in this case you can see that the blue line is positive only in the summer. So most of the time the sediment is taking away phosphorus and it's giving back phosphorus only in the summer. That helps to get insight in how your model is performing. A final example is this one, where we use the balances feature to quantify fluxes between subdomains. And in this case you see different subdomains, fluxes between them, and in every subdomain the picture shows the pollution loadings, the local loadings and the local processes. These mass balances are very useful for checking if your model is correct. If I'm very honest, I never ever made a mass balance and did not find an error or a problem in my model that I needed to correct. To recognize which processes are important if you're calibrating your model, to show the simulated water system functioning, to explain that to yourself or to your stakeholders, and all this is very useful. Finally, final subject of the webinar, I want to tell you a few things about how to use the processes library. The processes library is a collection of processes from a standard library which you can optionally expand with your own set of processes. That's what we call the open processes library. Individual processes in the library are activated from the input file because the input file contains constant input items which have the ID active and then the name of the process. And so only if this constant is present in your input file, the related process will be active. Processes that you don't activate do not affect your simulation. So whatever is in the processes library and you do not want to use is not bothering you. What is a process actually? It's a module which has input, which has output. Input can be state variables, hydrology, meteorology, parameters, or an output from another process. And output are items that you want to see to inspect if everything is going right, or input to another process, but most importantly, fluxes that are going into the processes term of DELWAQ. And you can organize your simulation in a way that you combine one process, two processes, 100 processes, and they all communicate with each other if necessary by this link that I showed here. The processes get their input either from your state variables or from your model input or from another process if it's available or from a default value. And some input to your processes evidently are automatically provided by DELWAQ, such as the time step if you need it, the volume of a segment, the flow, etc. Unfortunately, working with processes sometimes it becomes a little bit complex, and that has to do with what I try to show you on this slide. Because a process in DELWAQ actually consists of two parts. One part is the code, and that's generic program code for an individual process, and that is integrally linked into the executable in the way that Michel discussed you in the previous webinar. But there is also a process definition here. And that definition attaches names to the input and the output items for the generic code. Why do we have this separation? That's because certain processes are generic, but you can use them for different variables that you model. For example, the processes that you use for cadmium, a metal, you can use them for cadmium, but you can also use them for zinc and for lead and for mercury, etc. And so the generic formulations for any metal are here, and the names to use these generic formulations for cadmium, for mercury, and for all the other metals are here. And because of this definition, because of this double definition, the definitions are also part of the source code repository. And they are there, they are saved, and you can download them. And they are linked to your simulation by these two files that I mentioned here. If you want to use the processes library, you need to configure it. You need to select what parts of the processes library you want to use. And for that we have a processes library configuration tool, which is part of the Delft 3D and the SOBEC graphical user interface. And it helps you to select the state variables, the processes, the connections between the processes, the input items for your input file, and the extra output items you may want to see. This writes a subfile which is used by the user interface to produce parts of the input file. Now, I'm a little bit in doubt if I will do the demo or not. I think I will do a quick demo of the PLCT for you. One moment for me to load the program. I'm using an older version of Delft 3D. That's basically because I'm doing a project that uses an older version of Delft 3D, and yeah, that happens sometimes. This is the processes library configuration tool, and I will show you an example, a simple example. The first screen that you see here is a substance group screen. I will try to make an oxygen BOD model. If I select a group, I can enter it and select the substances from this group. I will simulate BOD and oxygen. Then you see here the selected substances. And by clicking a selected substance, I can see which processes the processes library offers. In this case, I will just select the mineralization of BOD. And for oxygen, you see that the same process is already activated because it's known that this process is affecting oxygen. But I will also activate the reaeration process of oxygen here. And for every individual process, you can edit it. And that means you see the input items for the process in a list here. And if you scroll down, you will also see the output items of the process. And this here shows you, for example, an input item, in this case the saturation concentration, which is you can either specify yourself as a constant or derive from another process, from the processes library. And because there is no default for this input item, the processes library, this configuration tool, automatically derives the saturation concentration from the other process. Some items you can activate as input items to your model, like this. For example, the reaeration constant. And in a similar way, you can activate output for the output of your model, like for example the saturation percentage of oxygen. I realize that this is not an exhaustive description of what this tool is doing, but it shows you the main things you have to select as a user. And the only thing I need to do now is save it, and then I generate files that can be imported in the user interfaces that provide input to DELWAQ, for example delft 3D and SOBEC. Again, there are lengthy manuals mentioning all the details of these tools to you. I can only show you a glimpse in this webinar. Back to the slideshow. This is a sketch of how it is working, the Processes Library configuration tool. It uses this processes definition that I showed you before to produce elements of your input file, and at the same time the processes definition is used by DELWAQ itself to produce input and to pass this information to the calculation program. And this definition of processes and how you select your processes is eventually reported to you in this input file, report file. So this report file gives you a general overview of your input, and this one specifically deals with the processes. I don't have the time to show you a demo of that, so that'll have to be skipped at the moment. The Open Processes Library was created to allow you to use your own processes library, to add your own processes to the DELWAQ Processes Library. There is a specific graphical user interface that supports you. It adds the process definitions to the DELWAQ process definitions, and it creates a framework Fortran code file that you can complete yourself with the processes you want to add to DELWAQ. These Fortran files are linked into a DLL and linked to DELWAQ 2 at the runtime. And again, there's a dedicated manual available that will help you do this if you want to do it. In view of the time, the only thing I can do now is show you an example of how we have used this feature in the recent past. And the example I want to show you is the transfer of heat between water flowing in a sewer pipe, and the sewer pipe itself and the surrounding soil. In this drawing you see a sewer pipe. Water is flowing through the pipe in a direction perpendicular to the screen, and we want to model the heat flowing from the water in the pipe through the pipe into the soil, and that heat can be stored in the soil and eventually given back to the water. For every longitudinal pipe segment, as you see it here, we divide the pipe itself in radial segments in this direction. The picture doesn't show it, but that's how it's done. We divide the soil in radial segments like this, and we divide the domain in tangential segments in this way. And because the problem is by definition symmetric, we only have to model the right half of the domain. The temperature of the pipe and the soil segments are modeled as inactive variables, so variables that cannot move with the flow. They are not transported with the water, they stay where they are. And the heat transfer between the water and the pipe and the soil was programmed in an Open Processes Library process. And the way we did it means that there is no longitudinal heat transport in the pipe and in the soil. A brief example, this is a network of pipes and branches used to test this feature, where this is the pipe where we model the heat transfer. So there are houses discharging wastewater to this sewer pipe, and we want to model the heat transfer as a result of that. And the next slide shows you an impression of what the results are. Here you see the pipe filling up with hot water, and you see that while the hot water is flowing through the pipe itself and the soil around it adopt the heat from the water. And you also see, if you look very carefully, that the transfer is only taking place where the water is, but that in the pipe and in the soil there is a circular transport happening from the lower half of the pipe where the water is to the upper part of the pipe where the water isn't. That kind of tricks you can do with the inactive substances of DELWAQ and the open processes library. That brings me to my closing remarks. We have touched a wide range of subjects, and I must admit that I'm taking more time than I thought I would take. And nevertheless, I'm happy that I'm able to finish within 55 minutes, and I've been trying to make you aware of the possibilities of deep water quality. The presentation plus the whole webinar will be available at our website. Don't know exactly when, but shortly. Tomorrow, Roderick is saying. And we will be more than happy to organize additional webinars on specific subjects in case you want it. Just let us know. And for that, please use our open source portal discussion group. And Christophe will be there to observe your requests and to do something useful with them. Next, I want to indicate again that there are different manuals that you can download. The Water Quality User Manual, an overview of all the processes in the processes library, a detailed description of the input file, and a detailed manual of how to use the open processes library. Then, not yet available for download, but appearing soon, is a detailed guide on the mass balances facility, on how to produce the mass balances output and how to interpret it, and the programmer's guide that will help you on some specific items, especially related to the more complex processes applications where you are programming complex processes. Soon to appear, that also means keep an eye on our website and you will notice when we will publish them. That concludes the webinar, at least my part of it, and we have just a little bit of time left for questions.
Yes, that's right. Thank you, Jos, for this presentation. Very interesting presentation. You've been asking quite some questions already to the panel. The panel was working really hard to answer them all. But there is some time left for an oral question. So if any one of you would like to ask a question to Jos, please raise your hand digitally. So this is your chance. So please raise your hand if you have a question. I see two hands appearing. Okay, I see a hand from Pushpa.
Yeah.
Pushpa, welcome.
Yeah, I am here. Yeah. So I am completely new to this subject, but I have a very basic question. So I am referring to the slide which showed with the estuary configuration. Okay? Can you hear me?
Yes,
I hear you.
yeah.
Yes, I hear you.
Okay.
I'm sorry, I should have responded. I'm going back to the slide.
Yeah, okay, I'm waiting.
This one.
Yeah, okay, yes. So now we have here 14 segments. Can you just simply tell me how we can define the size and the places, the orientation of this segment? Because, you know, if you look at, say, 14 and 13, so how we can define the boundary and the shape itself?
Okay, that's a good question. Actually, you will see from this picture, which is an old picture, that this is a one-dimensional model. The segments are aligned in one chain. For DELWAQ, the shape of the segment doesn't really matter. DELWAQ considers them. I'm trying to go back to. I'm going back to the segments now. What DELWAQ needs to know about the segment is its volume. So evidently the shape that you saw on the map impacts that volume. but just the volume will be sufficient.
Okay.
That's all it needs. And then on the next slide, you see that in those places where two segments are joining, are connecting, it needs information on how much water is flowing between the segments, the contact area between the segments, and also how long the segments are. So that is a kind of a translation you have to make as a user to make DELWAQ run this simplified model. Evidently, nowadays, you could also do it by using a 2D model, and then, okay, that's a completely different approach. But in this simplified 1D approach, that's the way to do it. Does that answer your question?
Yeah, thank you very much for your answer, and thank you very much for your nice talk. Thanks.
Thank you for being with us.
Thank you for your question, Pushpa. I see that we have another question from Mohammed.
Yes.
Hello, Mohammed.
I don't know if I am muted here.
No, you're not. We can hear you.
Oh, you can hear me? Okay. It was a very nice presentation, but you covered a lot of things. For a new user, I'm very versatile in groundwater, but I have not worked in surface water at all. Do you have a guideline of a series of webinars that will help me come up to speed of using DELWAQ? Today's one was a very introductory level of speech, but to be able to start using it, is there a series of webinars that you may suggest, or is there a document, a manual, which sort of guides the user by taking him step by step through a complete example, so that it becomes absolutely familiar of how this can be done?
Thank you for your question. It's clear. At the moment, what we have available for you are, let's say, what's the word? Tutorials for our 1D and 3D modeling packages that include DELWAQ. That means that it's not just DELWAQ, but that is a combination of a hydrodynamic model and a water quality model. And for both of them there are tutorials, and but that's the combination of hydrodynamics and water quality. As far as I know, delft 3D is freely available. Yeah, so you should be able to download that material, including the tutorial, and that will guide you through that will help you in the way that you just described. For SOBEC, it's not freely available, so that doesn't immediately help you. And there is no tutorial yet, not in a written form or in a webinar form, for the standalone DELWAQ. And that's if there are more persons that would be helped with that, then that's something we should consider for a follow-up webinar. It's maybe nice for other attendees to indicate via our website if they would be interested to have a tutorial webinar or tutorial document for a standalone application.
Yes, yes. I will. This is Mohammed again. I will make that request formally through your webpage. But at least from my perspective, that will be very helpful.
Okay.
Well, thank you, Mohammed, for your question. In addition to the answer of Jos, I can tell you that the webinar screencast will be available on the website, so let's say within 24 hours, so you can watch it back as many times as you want.
Yeah, that was the second question. Okay,
and also the presentation slides and the webinar screencast. And we have also set up a discussion forum on the website dedicated to DELWAQ. So if you have any questions about the DELWAQ software, please use the platform to post your questions and get in touch with the DELWAQ community. So I hope it helps you to get familiar with DELWAQ.
Thank you very much. That was
yeah?
great.
Okay.
Yep.
Good luck. I think there's time for one other question. Do you agree, Jos? Can you handle one more? We have a question from Luciana. Is it right? Are you still there, Luciana? No, she's not. Okay, I see that. Okay, we do another question. Rafael. Hello, Rafael. Rafael, do you have a question? Okay. Rafael, can you say something? Okay. Okay, then there's maybe one question from Muhammad.
Yes, I'm Muhammad Adnan speaking.
Welcome.
Can you hear me?
We can, yeah.
Yes. So my question is that I'm an hydrologic engineer, and I want to perform some study about the groundwater quality modeling in my PhD research. So my question is that for the can this model be applied on a basin scale for water quality modeling, just like the agriculture inputs impacts on the groundwater quality? And if it can be used, then there are also some other models like SWOT model and the mod flow. So where do you if I want to compare this model DELWAQ with those models, then at which place do you place this model in comparison to mod flow and SWOT models? Thank you.
Okay, thank you for your question. Easiest one is to rank this model to compare DELWAQ to mod flow. As far as I know, mod flow is a water quantity model or a hydrodynamic model for groundwater.
Yes.
So it is a different kind of model. It doesn't tell you anything about water quality. Mod flow tells you just the groundwater flows, and that would be input to a model like DELWAQ for groundwater. DELWAQ has not been developed for groundwater water quality modeling, and so there is no record of applications to groundwater. But there is recently we have started to apply it to a combination of surface water and groundwater on a basin scale, and that would make it comparable to a model like SWOT. But contrary to SWOT, DELWAQ has no track record in this respect, and we haven't documented it as a basin water quality model. So it's a fairly new way of using it, and whereas SWOT was specifically designed for catchment modeling, including soil, including groundwater, including surface water, and has a long track record and a very extensive documentation. So DELWAQ comes from a different field of application than SWOT.
Okay, so I understand that it is basically just like as you shown the example of the sewage water pipe. It is for like these things, like
for pipes, for surface water, for yeah, basically that's its comfort zone, I would say, and we are just starting to apply it in a catchment fashion like SWOT. And if you want, you can contact me via the open source website, and I can share some more details with you. But it's a fairly new sport, and I would say SWOT is much more has much more experience in that respect than DELWAQ has.
Okay, thank you very much.
You're welcome.
Thank you, Muhammad. I think we should leave it here. We're 10 minutes over time. So I'd like to thank Jos again for his presentation, of course, the panel for answering all the textual questions, and of course I would like to thank all the attendees of this webinar. Thank you for your attention. So as I just noticed, please keep on visiting the website for more webinars, and also use the community that we have been setting up to well, to get in touch with your fellow DELWAQ friends. Hope to see you back in one of our next webinars. Thank you. Bye bye.